Hi, everybody. Sorry, I just had a mouthful of food. It's like vanilla pudding. Um, okay, let's do some physics. Whoops. Okay, so we have all these different types of energy that we're going to be using in physics class. Well, several types in the universe. Here are the ones that we actually care about for physics. We care about this, and we care about that, and we care about that later on, and we care about this, and we don't care about this, or this in physics class. We care about it in real life. Now, we've been playing this bookkeeping game with energy, that the energy you start with is the energy that you end with, though it gets stored in different places in our accounting system, and some of those places we can't actually access, so the energy is effectively lost to us, even though it exists in the universe. What we want to do today is actually talk about the process by which energy transforms from one form to another. And we're going to start by looking at how forces transform energy um, from, say, kinetic energy into dissipated, or how when they accelerate objects, they're actually taking one form of energy stored somewhere else and turning it into kinetic energy. And so we're going to begin with the force equation, F equals ma. And we're going to basically follow these instructions here to do what you would normally be doing during a physics lecture, which is watching a professor just sort of passively while they explain what's going on. Instead, we're going to do the math ourselves to come up with a new formula. So we have here the instruction to multiply both sides of this equation by delta x. And now what we're going to do is, again, we want to look at F equals ma from a different perspective. Instead of looking at forces accelerating objects, we want to look at forces in terms of how are they transforming energy from one form to another. And the idea is maybe we can massage the F equals ma equation and come up with a way of looking at it through that lens. So we have F delta x equals ma times delta x, and now we're going to isolate a delta x on one side of the equation. So that's going to be v squared minus v naught squared over 2 equals a delta x. So let's go ahead and now do what it says to do. Substitute this into the formula you have in 2 on the right-hand side. So we're going to actually put in that v squared minus v naught squared over 2 on the right-hand side there. So we're going to get f times delta x equals m times v squared minus v naught squared over 2. Now what I'm going to do is I'm going to actually multiply this out. So I'm going to get f delta x equals mv squared over 2 minus mv naught squared over 2. And here's why we do this. It turns out our formula looks very much like this formula that we've written here. And now we're going to have some definitions. We're going to define this as work. So you can define it using a formula, which is F net times delta x. That's a great math definition. What it means in real life is how forces transform energy from one form to another. And typically, we define kinetic energy as 1 half mv squared, and the reason is actually it comes back to this formula. It turns out this is the definition of kinetic energy. It's actually defined in this formula. So we have kinetic energy final and kinetic energy initial in these equations. And so one way in which forces can transform energy from one form to another is by actually adding or taking away kinetic energy from the system. Just to be clear, there is a little bit of a sign convention. Positive work speeds you up, and negative work will slow you down, just so you know. So work is the means by which energy gets changed from one form to another. Now what we're going to do is we're going to do this in a little bit of a calculus way, because I want to show you a more general form of doing this. So we're going to repeat this exercise as a math exercise to actually show you a more general version of this formula. So we know that F net is ma, and it says, as you know, acceleration is the derivative of velocity. So let's do the substitution as indicated. So F is m dv dt. Now, here's the weird thing about this derivation that threw me off when I did it for the first time. Let's pretend that speed is a function of v. Sorry, speed is a function of position This was the suggestion that was given to me when I did this, and it seemed a little bit weird, but I'm just going to go with it. So if we want to take that derivative, they're doing a little chain rule thing here that I copied, which is v is a function of position, therefore dv dt would be dv dx times dx dt. So when we actually take a look at this, dx dt is just v. So when we follow this chain rule, we have f equals m times, well, you know what? Let's not get ahead of ourselves. We have dv dt equals dv dx times dx dt, but that's just v right there. So we have dv dt equals v times dv dx. Awesome. Let's substitute that back into our original formula. Okay? So let's do this. And we're told that there are going to be some limits. So we're going to actually do the following here. We're going to have f equals m dv dx times v. And let's multiply both sides by dx. So we'll have f dx equals mv dv. This is what they want us to do in 11 now. Let's write an integral sign on both sides and set the limit here from x naught to x final, and the limit here from v naught to v final. In other words, we're saying we're pushing this object over a certain displacement from x naught to x, and in that space it's going from speed v to speed v final. Once we evaluate this integral, what we're actually going to end up getting on the left side is, well, there's not a lot we can do with the left side. We're going to end up getting the integral of x naught to x final of f dx equals 1/2 m v final squared minus 1/2 m v initial squared when you evaluate the integral. So you need to do that antiderivative. There are some steps here. I expect you to do those steps. Okay. So now we have a new definition of work. This here and this here. So using the equation above, this is the integral form of the work kinetic energy equation. We have work is still change in kinetic energy, but now we're going to define work as f dx integrated from x1 to x2. So when we want to do a problem like question 14, it says suppose we have a force given by negative kx, where k is 4 newtons per meter. What is the work done by this force if the particle moves from 3 meters to 1 meter? Let's calculate this work if it started from 5 meters per second speed. So we have work is change in kinetic energy. So let's get the work. That's going to be negative k x dx integrated from 3 to 1. So I'm going to get negative k x squared over 2 from 3 to 1. So that's going to give me negative k over 2 minus negative 9k over 2. And that's going to actually then give me 8k over 2. And when I plug in k is 4, that's going to give me 16 joules worth of energy. So I know that 16 is the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. So now we can continue. 16 equals 1/2 times, you know what, I should have given you a mass. We'll make the mass 1 kilogram. So 1/2 times 1 times v final squared, which is unknown, minus 1/2 times 1 times 25, because that's v initial squared. So we're going to end up getting here, we can continue this over here. I'm going to continue it up here. So 32 equals v final squared minus 12.5. So I have 44.5 equals v final squared. So when I solve for v final, I'm going to end up getting something. I'm going to approximate here. Check this with your calculator. Around maybe 6.6, 6.7. Let's just see if my guess is even any good. Oh, not bad. I got 43, so around 6.6 meters per second. All right, that might be one that we need to go over in class after we do our appraisal, our quiz. So in the next video, I will actually be doing the 2003 problem, and then I'll be doing the 2013 problem that you're going to be quizzed over on Friday.